Hello everyone, and welcome to the course of NanoBiophotonics, touching our daily life. So, this is the week 4th discussion, and I am Udiptya from IIT Madras. I will be taking the problem solving session. So, coming to coming to this week, this week's sorry, this is the week 4th. Typing mistake, but what we learned is basically interaction of light with cells. So we in this chapter we learned a lot about the uh, photobiology, which is basically the interaction of light with biological matter. So we have seen the interaction of light with matter. So it's kind of a specialized discussion on how the interaction happens and what it means. So uh, so basically the chapter was all about various interactions with molecular, cellular and tissue components with light, and then we'll also learned about some light induced radiative and non-radiative processes, and which are like also a lot of various photochemical processes like photochemistry, yeah, then photosensitizers, yeah. so so this photo processes, like for example photosynthesis example, play a major role in our biological function. Also, we also discussed about the the formation of vitamin D in the body due to the sunlight. Yeah. Also, there are some cases like you have some forms of cancers developing just because you are exposed to light radiations of light in the UV range, which can lead to cross-linking of your DNA bases. So that is the core of how this light can affect the cells. So we also learned about different light absorbing components, yeah, endogenous and exogenous. So basically endogenous basically are the cells itself, yeah, the DNA, RNA, proteins, yeah, and then exogenous are something that are added to absorb light or in it. So some green fluorescent protein or such, which are used quite widely in biological experiments. So yeah, so lot of photo processes that we saw, yeah, about like photo addition, photo fragmentation. So like if you divide the if you divide the light absorption, yeah, light absorption as such, uh, light absorption by cellular components, okay. So we can have two: radiative and non-radiative. So in radiative it comes as fluorescence, yeah, and non-radiative you can have either the thermal effects and photochemical. So in the thermal effect you can have basically due to in cases where you have higher thermal effect, you can also lead to protein denaturation or water vaporization, yeah. So this can lead to the loss of the structure, and which may have impact on the component or structural. So proteins can denature, and it may lose its enzymatic activity. You can have water vaporizing because of thermal effect, and then the structure will be disrupted. But then coming to photochemical processes, you have multiple photochemical processes, yeah, like photo addition, photo fragmentation, photo oxidation, photo hydration, isomerization and photo rearrangement. So a lot of chemical reactions that go upon light induced processes. Yeah, so we learned about those processes, uh, like and saw what can be the thing. So yeah. Then going to spectroscopy. So spectroscopy is um, quite a wide field and explored a lot by the chemists as such, but a good characterization and analysis tools. Yeah, analysis tool it is. So when it comes to the spectroscopy as such, the spectroscopy is primarily uh, so it draws its core from light matter interactions here. So uh, the interaction, basically the interaction of light at the molecular level, it can produce absorption, spontaneous emission, stimulated emission, and Raman scattering that we learned, yeah, as described. So and at the bulk level, it produces absorption, refraction, reflection, and scattering due to the propagation of light through bulk sample. And as a result, it can also have various photophysical and photochemical processes. So this major branch of interaction of light and matter is spectroscopy. So this spectroscopy only involves the study of a transition between the quantized levels. Yeah. So you have different kinds of spectroscopy that we saw. Yeah. The UV visible spectroscopy, we essentially deals with the transition in the electronic states. Or you have IR spectroscopy, which deals with the transitions in the vibrational states of molecules. Yeah. So like then you have Raman, which also has like vibrational transitions. And this usually is this quantized, this spectroscopy is such that it depends on the nature of the light. Yeah, so it depends on the energy that you are providing. So as we know, so there are like you energy gap, yeah, in between the, like you have an atom and then you have different shells, K, L, M, N. So it usually depends. So if I give a light, give a energy that is particular, and that gap is same as the gap between the two shells in the form of a atom, then it can absorb that energy, take up that energy, and go to the higher state. Like from K, it can jump to the L shell. So there, and then it can stay there and come back to the ground state to buy. So then you have this absorption of energy and going to the another state, you will see there we will see the loss of energy or absorption in the energy. So that's how in electronic. But when you are working with bulk materials, this is like atom, you are talking about shells. When you talk about bulk material, you usually talk it in terms of the bands, yeah, conduction bands, and the valence band. So this valence band is nothing but the ensemble this KLM shells, ensemble of all these states together to form a band of energy. So yeah, so in from a spectroscopy usually so in spectroscopy what we usually do is what we usually do is so in this spectroscopy what we will do is we have as such, yeah, this this may be the valence band, and this is the conduction band. So there will be electrons here. Yeah. So if you provide enough energy equal to this energy gap, so electrons will jump here, jump to this state to this state, and after that this may stay there for some tens of nanoseconds, and then it will come down to the ground state. That's what happens. Yeah. So if you provide the energy only in this zone, then only it will absorb. That's the core of spectroscopy. So depending on the type of light, like if you have visible light shining on visible light, then you will have transitions in electronic transition between two electronic states. Okay. If you are giving IR light, so it will lead to absorption of IR photon to go from a lower to a higher vibrational level. In case of Raman, it usually is a scattering of a photon in the visible range to produce a vibrational state change. So Raman, it's bit different. So as type of electronic transitions, we learned about the like different types of electronic transitions, like sigma star transitions, DD transitions, pi star transitions, and to pi star. So the molecular orbital transitions that we learned about. Yeah. Now coming to bioimaging, which essentially is so it forms a major thrust of biophotonics. Yeah, major chunk of work in biophotonics. So it involves study of wide range of biological specimens, starting from cells to tissue samples to in vivo imaging of live objects. So the optical bioimaging, you can imagine that it can start from broad range of length scale, from sub-micron sizes of virus, yeah, which are like this COVID essentially was around 100 nanometer size, to bacteria, to microscopic sized biological species. So in optical bioimaging, you usually utilize optical contrast, such as difference in light transmission, reflection, fluorescence between the region to be imaged and surrounding region, like to have a contrast. The various optical bridges involved and microscopic methods that are used to enhance this contrast were discussed. So you also learned about the optical coherence tomography, yeah, which is a interferometric method, which enhances contrast and reflection geometry, and it is one of the important techniques for three-dimensional imaging. So a lot of other microscopic developments, like near field scanning microscopy, which can help obtain images at a resolution of 100 nanometers, like, which is a bit difficult because it is much less than the wavelength of light itself. Then you have total internal reflection fluorescence microscopy, which uses evanescent excitation of fluorescence, and it can be used to fluoresce or excite fluorophores which are in the vicinity of the surface. Yeah. So we understand that bioimaging, it is an important biomedical tool, like X-ray imaging, then MRI, ultrasound. Yeah, these all are like very much useful and very much used nowadays for the biomedical applications here. So if we draw like a classification classification of all the techniques available. Yeah, if you draw it, it will look somehow like this. So if we have optical imaging, if we have optical imaging in the top, so it can have different fades. Yeah, optical imaging can be of transmission, it can be a reflection, or it can be fluorescence, usually of this nature. Yeah. So here you will have some techniques like confocal microscopy, then you have polarization gating, time gating, and some frequency domain methods. So it is basically this transillumination is utilizes a spatial variation of absorption and scattering in the microscopic and microscopic. So different tissues, like you have tissues, so it will have different zones. So that different zones, some zones will be absorbing more or scattering more. So you will see the contrast. So some these are some of the algorithms or methods which can enhance those reflection. Then you have the same reflection, confocal working on reflection method, and OCT, yeah, optical coherence tomography. In fluorescence you have confocal too, yeah. Then you have FRET. Then you have something called as time resolved lifetime time resolved fluorescence lifetime imaging, called as FLIM. So yeah. So a simple microscope usually comes in transmission form of microscope. Other mostly the microscope is like simple and compound microscope will come in this. So we also looked on resolution, readings, yeah, and then going back, coming to fluorescence microscopy. So fluorescence microscopy has emerged as a major technique. Like, so fluorescence emission is dependent on specific wavelengths of excitation of light, and the energy excitation under one photon absorption is greater than the energy of emission. So the wavelength of excitation light is always shorter than the wavelength of emission light. But why fluorescence became so used? It is because of the advantage of providing a very high signal to noise ratio. So it enables us to distinguish, have a great distinguishing for spatial distribution. Yeah. So some tissues you want to image, so it will have a very good spatial distribution of even low concentration of species. So this fluorescence, to use fluorescence you can go for two modes. One is you utilize the endogenous fluorescence, so autofluorescence. So or you may label the specimen, a cell, a tissue or a gel with suitable molecule, which is basically called a fluorophore. So or a fluorochrome. So whose distribution will become evident upon illumination. So this fluorescence microscope is ideally suited for the detection of particular fluorochromes or fluorophores in cells and tissues. So coming to the fluorescence microscope that mostly people use, that is it follows the basic epifluorescence excitation, and it utilizes filters and dichroic beam splitter, which is essentially packed inside a fluorescence cube. So what happens is the object that you want to image is illuminated with fluorescence excitation light through the same objective lens that collects the fluorescence signal for imaging. So a beam splitter is present, which transmits or reflects light depending on its wavelength, and is used to separate the excitation light from the fluorescence light. Yeah, so that's the work of the fluorescence cube. So to make it more understanding, so if we have so this epifluorescence, epifluorescence, usually has so if this is the so epifluorescence, if we talk about, so it will have, so if we consider this as the focal plane, okay, so we have a objective over it, and then we have a beam splitter. So what happens is light is excited from this side. Yeah. So this beam splitter will put the light, incident the light on the sample. Yeah. And from this sample, the light again will go back to the beam splitter, and now this will allow the light to go, and which you can monitor this light, you can observe this light. So emission happens here and excitation from this. So this is the epifluorescence setup. And then we saw some applications, so yeah, that on OCT and a lot that we saw. So we will go to the problems. So a scan in OCT, optical coherence tomography, refers to, so you will have 5 minutes to answer, and then we will discuss the answer. So the answer is axial scan. So A scan in OCT refers to axial scan because it measures the echo time delay of backscattered light from different depths within a sample along the axial direction. So that's how that contrast comes from here. So A scan is for axial scan. Which spectroscopic technique is commonly used for non-invasive monitoring of tissue oxygenation? So it is near infrared spectroscopy. So near infrared light is particularly interesting in non-invasive monitoring of tissue because biological tissues relatively this NIR light, yeah, usually penetrates relatively well compared to the other wavelengths of light. So we use NIR spectroscopy, non-infrared, near infrared spectroscopy for non-invasive monitoring of tissue oxygenation. Which of the following is an application of clinical spectroscopy? So the answer is all of the above. Clinical spectroscopy offers a powerful set of tools for non-invasive and minimally invasive analysis of biological samples helping which helps healthcare professionals make informed decisions for disease diagnosis, treatment, and patient care. Which of the following technique is commonly used for clinical IR imaging? So the answer here is FTIR spectroscopy. So FTIR is a technique which is commonly used for clinical IR imaging due to its high sensitivity and non-invasive nature and the ability to generate real-time, level-free and high-resolution infrared images of tissues. enabling comprehensive tissue analysis and disease diagnosis. So, as you remember, IR was all about vibrational, yeah, vibrational spectroscopy on molecules. So, it is a good technique for high resolution infrared imaging of tissues. Which of the following is an advantage of confocal macroscopy over conventional wide field microscopy? So it's all of the above. The advantage of confocal macroscopy over conventional wide field microscopy is its ability to eliminate out of focus light, resulting in improved optical sectioning and higher contrast in three-dimensional imaging. This allows for sharper, more detailed images and better visualization of cellular structure, especially in thick specimens. All of the above. The diffraction limit in optical microscopy is commonly described using the So the answer is airy disk. Airy disk, which is the central spot, is in the point spread function resulting from the diffraction of light as it passes through the circular aperture. So it represents the smallest resolvable spot size and sets a fundamental limit on the ability to distinguish closely spaced images in the image. Yeah. Fluorescence resonance energy transfer occurs when the donor molecule So it's about infrared. It transfers energy to the acceptor molecule through the non-radiative process, and it is that's why very sensitive to the distance involved between the acceptor and the donor molecules. Yeah, so it is very much sensitive to the distances. Which type of vibrational modes provide the most intense Raman scattering? So it's asymmetric stretching. So it involves a change in the molecular dipole moment during the vibration, resulting in large change in polarizability and hence a stronger interaction with the incident light. This leads to a higher Raman scattering cross section and more pronounced signal intensity in the Raman spectrum. Which of the following is an common example of a photo-oxidation reaction? So it's rusting of iron. Rusting of iron can be enhanced by the presence of light, particularly in the UV region. The UV light can initiate photo-oxidation reactions by providing energy to break chemical bonds and create reactive oxygen species that accelerate the oxidation of iron, leading to the formation of iron oxide or rust. So this is a numerical. Consider two microscopic setups being used at a 700 nanometer wavelength. Suppose for one setup the numerical aperture of objective 1 is 0.8 and for the other setup numerical aperture objective 2 is 1.25. Which setup is a finer resolution? So okay, so I'll solve it. Okay. So formula for resolution, I'll recall it's like if you consider D as a resolution of a microscope, so D equal to lambda by 2 into NA. NA here is numerical aperture. So it is given that lambda equal to 700 nanometer and numerical aperture is given for two respective ones. So the first one is 0.8 and Na2 is 1.25. So we have to calculate the resolution of both the setups. So for first one, D1 equal to 700 into 2 into 0.8, which comes to 700 divided by 1.6, which is 437.5. So this 700 is nanometer, so this will be in nanometer. For 2, similarly we'll go for D2 equal to 700 divided into 2 into 1.25. So it will come out as how much? 1.25 into 2 is 2.5. Yeah. So 2.5 equal to 280. So we know that D2 is smaller than D1. Yeah. So the second setup will yield a finer resolution here. So that's all for today. If you have any doubts, you are free to ask. Others can leave the meeting. Thank you. We'll meet again we'll meet again at the same time the next week. Thank you.